Hello, welcome to the Math 159 Gould Chapter 6, Section 2 video about the normal model. Alright, so what is the normal model? Well, by model, remember that, oops, model is another name for a probability distribution. So the normal model is the normal probability distribution. It's a particular probability distribution. And it is a probability, a very commonly, it's a very commonly encountered probability distribution, or it's very commonly encountered in nature, and we'll talk about some examples, for continuous numeric variables. Alright, so let's talk about it. So, two properties that you're going to notice right away when you look at some examples are that it is unimodal and symmetric. So I'm going to quickly transfer us over to... So I'm going to change us over to StatCrunch, and we're going to look at an example. Okay, so what we have here is some data from the Haynes dataset. It collects things about, like, let me select this, the sex of the person, their age, their race, their marital status, their weight, all sorts of stuff. So anyways, lots of different things. We're going to be interested in particular at weight, and you can also see they have pulse rate, systolic, and diastolic blood pressure. So we're gonna look at some graphs. I'm gonna go graph, histogram. There we go. And we're gonna look at weight. Oh, sorry, height, not weight. We want height. So looking at this, you can see you have a high point right about here at around 170 centimeters or so, and you can see the right tail is about as long as the left tail, so it's fairly symmetric. It's definitely unimodal. And then we're also going to look at diastolic blood pressure. And you get a similar sort of shape. A high point right here at about between 70 and 80, and discounting those outliers, it's actually pretty symmetric. So looking at these two graphs, there's some similarities about them. They're both unimodal, they're both roughly symmetric, and I guess we can look at one more. Let's look at cholesterol. Or pulse. Let's see pulse. Not as good as what I wanted. Let's do cholesterol. Graph, histogram. Oops. Cholesterol. And, well, if you were to ignore these outliers over here, again, definitely unimodal, fairly symmetric. But looking at these two, these are pretty good examples of normal distributions. Okay, so let's go back to the notes, and we're going to tell you some stuff. There we go. Okay, so definitely unimodal and symmetric. So remember, when we're looking at numeric variables, their distributions, there's several things we want to look at. We want to look at the shape, whether there are outliers, the center, and the spread. Now, we've already looked at shape. The shape of normal distributions are unimodal and symmetric. Normal distributions should have no outliers in general. Okay, so when you look at a histogram for something that you think might be a normal distribution, it should appear to be roughly unimodal and symmetric, and there shouldn't be any outliers. So let's talk about spread now, center and spread. So you might recall from, I think it was chapter 2, if you're dealing with a unimodal and symmetric distribution, you want the center to be measured by the mean, and you want the spread to be measured by the standard deviation. And we have two special symbols for these. Whenever we're looking at the mean, we use the Greek symbol mu, sort of like the Pokemon. And then for standard deviation, we use sigma. And the normal distribution is actually really interesting. If you know the mean and standard deviation, you know everything you need to know about the distribution. So these distributions are interesting. If you have those two pieces of information, their mean and their standard deviation, you can calculate anything you need to know about it, which is pretty cool. So because of this, whenever we're dealing with normal distributions, we have a particular way of talking about them. We use the large letter N, and then we enter in parentheses what the mean is and what the standard deviation is. So for instance, let's say our variable is the heights of adult males in the United States. And you remember we looked at height, and it was roughly, we looked at height from the Haynes data, and it was roughly symmetric and unimodal. It appears to be a normal distribution. If you wanted to model the heights of adult males in the United States in inches, the average or mean height is about 69 inches, which is about 5'9", with a standard deviation of about 3 inches. So this is telling us, hey, heights of adult males in the United States has a mean of about 69 and a standard deviation of about 3. Okay, so now what we're going to talk about is, well, what changes if all you need to know about the normal distribution is the mean and the standard deviation? What happens if you change them? So what happens if you change the mean or standard deviation? Alright, so let's look first at standard deviation. And let me draw some stuff. Actually, let me also put on, I keep on getting mail notifications, so I'm going to put on, what's it called, the thing to focus. There we go. Stop showing these to me. There we go. Okay, so what happens if you change the standard deviation? So first of all, when you're looking at a normal distribution, the probability density curve is what we call bell-shaped. So this sort of looks like those histograms we looked at earlier, but smoothed out. So we have this hump in the middle, the tall hump. That's your mode. It's unimodal. That would be at the value of the mean. So what happens if you change the standard deviation? Alright, so let's look at the effects. So if you change the standard deviation, it's going to affect the height. Two things. One of them is the height of the bump where the mode is. So it's going to make this bump over here where the high point at the mean, either shorter or taller. And we'll talk about how that works in a moment. And it will also affect how wide the whole thing is. So let's say that you make the standard deviation smaller, a smaller number. So do you see how, for instance, the standard deviation is 3 here? Let's say that you decreased the standard deviation to 1, made it a smaller standard deviation. What you would, because that means that it's less spread out, the probability density curve will be more concentrated. Everything will be more bunched in the middle near the mean. What that means, in other words, you're going to have a larger hump, or whatever you want to call it. So what might happen is your graph would look something like this. So it'll be taller and thinner. It's more concentrated. What happens if the standard deviation became larger? Let's say you increased the standard deviation from 3 inches to 8 inches or something. Well, now it's going to be more spread out, because remember, standard deviation is a measure of spread. It's more spread out, so you're going to have a smaller hump. So what you're going to get is, it's going to look sort of more like this. Everything is going to be less concentrated. It might look more like that. So if you decrease the standard deviation, it becomes taller and thinner, but everything is more near the middle. If you increase the standard deviation, that hump becomes shorter and everything is more spread out, like you squished something. Okay, cool. And we can actually, there's some ways to look at this on StatCrunch, so we're going to switch over to there. And it's called simulation. So what we're going to do is I'm going to open up a new StatCrunch, new data table. And what you can do is you can go data, simulate, and you can see right here it says normal. So I want, let's say we're going to make 100 heights. So we're going to put 100 rows, one column. And we're going to look at, let's say the average is 69, and we're going to look at standard deviation of 3. So there's my 100 heights with that standard deviation. And I'll go data, simulate, normal, 100 rows, one column, same average, 69. But now we're going to increase the standard deviation to, I don't know, 20. So remember the first normal distribution, so we'll call this one normal 1, and the other one will be normal 2, and we'll put wide because it was standard deviation was 20. So we're going to compare the graphs. We're going to go graph, histogram. We're going to select the two of these. So it's going to show the two of us. Actually, let's see if we can see them side by side. Can we make it so that we see them at the same time? Unfortunately not. Okay, so here was the first distribution. You can see that the high point is pretty close to 69, and it goes out to 60 and 80. Now let's go to the next one. You can see that the high point is right here, in between 60 and 80, and it's much more spread out. It goes all the way out to 120, right? Before it only went out to 60 and 80. This one goes out to 20 and 100. You can see that literally the graph has become more wide by increasing the standard deviation. You can see it says normal to wide right here, right? That's the data that was simulated. These are basically heights. If we go look at the data, this first column from normal 1, someone was 71 inches tall, someone was 64 inches tall. Same thing over here. So we changed all of it, and you can see that it literally becomes wider. Okay, so let me switch back to the notes. Okay, so now we're going to talk about how do you calculate probabilities with these things. Calculating probabilities. Okay, so let's say that you were dealing with heights of American adult males, mean of 69 inches, a standard deviation of 3 inches. So I'm going to draw our normal distribution, the graph. So here's the height right here. They're all normal distributions. When you draw them, you just draw it like a hump like this. And then what you do is you mark the mean in the middle. So I'm going to put 69 inches. Boom. Okay. So let's say that we want to know, hey, what's the chance or the probability that someone's height, and remember height is modeled by this normal model of 69 inches for the mean and 3 inches for the standard deviation. What's the chance that they are taller than 60 inches? So what does that mean over here? So remember 60 inches is 5 feet tall. So 60 inches would be about over here somewhere. So the probability that we're interested in is actually the area under this curve to the right of 60 inches, because we are interested in heights greater than or equal to, so we would shade to the right. If it was less than or equal to, we would shade to the left. Or let's draw another one. So it's actually, when you're calculating these probabilities, I highly recommend that, so the problem will be given to you like this. You should draw a graph. So if they're asking, hey, what's the chance that the height is greater than 60, you would draw the normal distribution with the appropriate mean, find this is called the value. We're interested in our value being greater than 60, so you draw where 60 is in relation to the mean, and then shade in the correct direction. So here's another normal distribution of height, again with the mean of 69 inches, and let's say we were interested this time in, hey, what's the probability that someone's height is between 64 and 68 inches. So remember 64 inches, that would be 5'4". This would be 5'8". So we're asking, hey, what's the chance that if you randomly choose an adult American male that their height is between 5'4" and 5'8"? So 64 inches would be like over here somewhere. 68 inches would be over here somewhere. And we want to know what's the area under the probability density curve between 64 and 68. So StatCrunch actually makes this quite easy for you to do. So I'm going to move us over to StatCrunch. Okay, so what you're going to do is you're going to go to Stat, and there's a thing called Calculators. So this helps you calculate probability. And you can see there's lots of different distributions, but we've only learned the one, the normal distributions right down here, and here past the middle a little bit. And then this will pop up. So what you need to do is you can see it has places to enter the mean and the standard deviation. So our mean was 69 inches, and our standard deviation was 3. And you have two choices, standard or between. So I'm going to choose standard, because we want to know what's the chance that x, which is the variable, is greater than. You have to switch between less than or greater than. So greater than, what was the first one? 60 inches. And you click compute. So you can see 60 is over here, and it's centered in about 69. So this is telling us that given our distribution, the chance that a U.S. adult male is taller than 5 feet, this is a decimal, is 0.99. So in other words, a 99% chance. Almost all men you meet are taller than 5 feet tall. To calculate the other one, we would click between. Do you see how now it gives two numbers? Remember, the lower number was 64. The higher number was 68. And you can see it shaded it for us, right? There's 65 right there. You can see it starts to the left of it a little, and then it goes all the way over to 68. There's about a 32% chance. A 32% chance that a random U.S. adult male that you encounter is between 5'4" and 5'8". Now I want to draw your attention to these numbers right here. It says 68, 95, 99.7, 99.7 ticks. What those are the, remember from the empirical rule that 68% of your population will be within 1 standard deviation, and 95% of your population will be within 2 standard deviations. It changes the tick marks. So you can see that the mean is 69, and the standard deviation is 3. If you go 1 standard deviation away from 69, you'll subtract or add 3, which will put you to 66 and 72. You can see that on the x-axis there, the horizontal axis. So these give you standard deviation tick marks, right? So if you start at 69, you go left 3, you get to 66. You go left 3, you get to 63. You go left 3, and you get to 60. So and you do the same thing from 69 to 72 to 75 to 78. You might recall that basically everyone is going to be within 3 standard deviations, which is why these tick marks stop at 3 standard deviations and don't go any further. Okay? So let's go back to StatCrunch. I have some more things to show you. Okay, there is a special normal distribution that you'll encounter called standard normal distribution. That's the normal distribution where the mean is 0 and the standard deviation is 1. And this is important because it's actually, remember how we calculated z-scores? The standard normal distribution is what z-scores are. So you might recall a while ago we talked about how the lengths of pregnancies are normally distributed. The mean pregnancy is about 280 days long, and it has a standard deviation of about 7. So let's say you want to know, you're talking about someone who had a pregnancy that was 287 days long. That's a bit longer than average, which would be 280. And you can take that value of 287 and calculate a z-score. How would you do it? Well, you would do the value, which is 287, minus the mean, which is 280, all divided by the standard deviation, which is 7. And if you calculate all that, you get 1. So what ends up happening is that this value of 287 in this normal distribution is equivalent to this z-score of 1 in the standard normal. So z-scores are a way of taking any distribution, like from the one we just talked about, and converting them all to a similar thing, which is the standard normal distribution, which has a mean of 0 and a standard deviation. Okay, so we have one more topic for this section, which is percentiles. And this is an interesting topic. The way it works, oh, that keeps on getting stuck, whatever. The percentiles, so a percentile is a value such that a value that is larger than a given percentage of the population. So let me give you an example. What is the 18th percentile? The 18th percentile is a value which is larger than 18% of the population. So this is sometimes called inverse probability, and I'll explain why. So normally you would say, hey, I want to know what the probability that someone's height is greater than, I don't know, 64 inches. And I'm just going to make this up. It's like 66%. Okay, so let's draw a little picture. Okay, so remember our mean was 69. And we found out here the 64 is right here. And if you calculate the percentage to the right of that, that's 66%. But with percentiles, we want to know the value, what it's larger than. So if here's 64 and 66% is greater than that, then what's 100 minus 66? You're left with 34. So if 66% of the population is taller than 64 inches, that means 34% is shorter than 64 inches, which means 64 inches is the 34th percentile. So when we're calculating probabilities, I'll give you a value, like 64, and then we calculate a percentage. With inverse probabilities, it goes backwards. I give you a percentile or percentage. So we're told, hey, or let's say that in this case 34th percentile. I would tell you, hey, what's the 34th percentile? That's a percentile. And then you have to figure out a value that makes that true, which is, in this case, 64 inches. So I'll show you how to do this on StackCrunch. It's actually pretty straightforward. Use the same thing. So let's switch over to StackCrunch. Okay, so you use the same calculator. So what you're going to do is you enter your mean, you enter your standard deviations, erase these two numbers over here. So if you're going to do percentile, you need this to be less than, because you want to find the value over here that a given percentile is less than this. So we're going to put in 0.34. That would help me find the 34th percentile. Press enter, and here's the number over here. So according to this, if someone 67.7 inches is the height such that 34% of people are shorter than that. Okay, so this is so last time you might remember we entered the value and then it spit out the percentage over here. When you're given a percentile, you put the percentile over here, and you need to make sure that this is less than and it shades to the left, because that's how percentiles work. Okay, and this is the end of the 6.2 video, chapter 6, section 2 video, and I'll look forward to doing the next one soon.